Welcome back to this next video in which we are discussing Eisenstein's criterion. Okay, so in this video what we're going to do is provide a proof of Eisenstein's criterion, but just before we do that, what I'd like to do is rewrite out Eisenstein's criterion, because in the previous video what I did is made a slight mistake when I actually wrote it out. I said it correctly, but when I wrote it out I made a very small mistake, so I would like to rewrite it out on a fresh sheet of paper here and make sure it's correct. Okay, right, so we are dealing then with a polynomial p of x in our ring of polynomials over an integral domain. Okay, so it's in our R adjoin x here, and remember this polynomial must satisfy two conditions. Firstly, it is non-constant, okay, so it's not a constant polynomial, and in addition it must be a monic polynomial, i.e. the coefficient of the highest power term must be 1, okay, the leading coefficient is 1, okay, and if it obeys those two criteria, we can apply Eisenstein's criterion to it. Okay, so Eisenstein's criterion then says that this polynomial will be irreducible, okay, or at least you can show that it will be irreducible if it is true that there exists some prime ideal p, okay, which is a prime ideal of your coefficient ring, the integral domain capital R, such that all of the coefficients of the polynomial p of x, apart from the leading coefficient, are elements of that prime ideal. So p0, p1, all the way up to pn minus 1 are elements of that prime ideal. However, the constant coefficient p0 is not, and this is where I made the mistake previously. I didn't put that is not an element, I just put is an element of p squared, so I put the exact opposite of what you need to put there. Okay, of course I said it correctly, but I didn't write it correctly. So p0 is not an element of p squared, which is the set consisting of all of the elements of the prime ideal capital P multiplied with another element of that prime ideal capital P. Okay, so this then is a way that you can prove that a certain non-constant monic polynomial in a ring of polynomials over an integral domain is irreducible by finding such a prime ideal which satisfies those two things. Okay, and we did an example. Now what I want to do is actually prove that this is true. Okay, and the nice surprise is that actually this isn't too difficult to prove at all. In fact, it's very easy to prove. Okay, all that it really is going to rely on is you having a good understanding of what it means to take a polynomial modulo an ideal. Okay, and if you're not totally familiar with that, we do have a video further back in the playlist on ring theory concerning polynomials modulo an ideal. Okay, so watch that to brush up. Okay, so let's begin then with the proof. Okay, so what I'm going to assume then is that we have a non-constant monic polynomial in the ring of polynomials over our integral domain, and that we have found a prime ideal p such that this is true, such that all the coefficients apart from the leading coefficient are in that prime ideal p, and the constant coefficient is not in p squared. Okay, and I'm going to now prove that that implies the polynomial p of x is irreducible. Now how am I going to do this? I'm going to do it by proof by contradiction. So I'm going to assume the exact opposite of what I hope to prove. I'm going to assume that the polynomial is reducible. Okay, reducible in the ring of polynomials over the integral domain, and then arrive at a contradiction. And the contradiction I'll tell you now that I'm going to reach is that the constant coefficient p0 is in the element, is an element of the prime ideal squared, p squared here. Okay, and therefore it will contradict the fact that I've already supposedly found a prime ideal for which this was true. Okay, right, so let's go. Okay, so what's my first step then? So if my polynomial p of x is reducible then in the ring of polynomials over the integral domain, then that means that I can write it as one polynomial which I'll call a of x times another polynomial which I'll call b of x, where both of these are non-units. Okay, so this is a non-trivial multiplication here because both of them are not units. So if the polynomial is reducible, then by definition you can find such a factorization into two non-unit elements being multiplied together to give the polynomial p of x. Okay, and I also can claim that I can conclude that these polynomials a of x and b of x are also non-constant polynomials. Okay, now that's not as trivial as you might instantly think. You might think that I can conclude that because, of course, all constant polynomials are units, but that's not true, okay, because we're working in a polynomial ring over an arbitrary integral domain. Okay, so it is not true necessarily that all constant polynomials are units. Okay, what we can conclude is that all non-constant polynomials are not units, but we can't conclude that all constant polynomials are units. If we're working in a polynomial ring over a field, of course, we'd be able to conclude that, but we're not. We're working in an arbitrary integral domain, so there will be some potentially constant polynomials that are not units. Okay, but I still claim that I can conclude that a of x and b of x are non-constant polynomials. So what's my reasoning for that? Okay, well the reasoning is that this polynomial p of x here is a monic polynomial. Okay, that's what's going to be important in being able to conclude this. Okay, the fact that this is a monic polynomial and the fact that both of these are not units is, I claim, going to show me that they are non-constant polynomials as well. So what's my reasoning behind that? Okay, well the reason I can conclude that is, let's suppose that one of them was a constant polynomial. Okay, so let's suppose that a of x here was a constant polynomial, let's say a here, and then if I consider this being multiplied by the polynomial b of x, which will be b0 plus b1 of x plus all the way up to, let's say, bn x to the n, it will have to have the same degree as the polynomial p of x. Then let's have a look at what this result of this multiplication would actually be. Well, of course, I'd end up with a multiplied by bn as my leading coefficient of the polynomial p of x. Okay, but of course the leading coefficient of my polynomial p of x is 1 because the polynomial p of x is monic. So that would now imply that bn here was the multiplicative inverse of a in the coefficient ring capital R, and that would imply that a was a unit in the coefficient ring capital R, and therefore a was a unit in the ring of polynomials over the ring capital R. Okay, so that would then imply that a was a unit. So if a was a constant polynomial, you could also conclude that it had to be a unit because the polynomial p of x was monic. Okay, so now what I can show, therefore, is that both of these polynomials are non-constant polynomials. Okay, right, so I can conclude successfully that a of x and b of x must be non-constant polynomials, otherwise, if one was a constant polynomial, it would be a unit, and I've assumed that they're not units. Okay, right, so they're also non-constant polynomials. So where do I go now? Okay, well what I'm going to consider is taking polynomials modulo a certain ideal, in particular this prime ideal p here that I'm given exists. Okay, so what I'm going to consider then is the homomorphism, which will map all of the polynomials in the ring of polynomials with coefficients in our integral domain capital R onto the ring of polynomials with coefficients in the quotient ring R quotiented out by p. Okay, so this ring of polynomials, this is what it means to take polynomials modulo a certain ideal. Okay, what you do is you take a polynomial and it will have lots of coefficients from the ring capital R here, and what you say is, okay, that coefficient, you do this for each of the coefficients, you say what coset in the quotient ring R quotiented out by p would that coefficient end up in. So you map the coefficients of the polynomial onto what they are modulo the p. Okay, what they are in the quotient ring R quotiented out by p. Okay, so you turn the coefficients into the cosets that are in this quotient ring R quotiented out by p. You take the elements here and turn them into elements here. Okay, and you end up with a polynomial where the coefficients are from the quotient ring R quotiented out by p. Okay, and we explore this homomorphism in far more detail in the video on polynomials modulo an ideal, and we prove that it's a homomorphism. Okay, right. Just to tell you a few things that are going to be important later, just to get them out of the way. Because the polynomial, because the ideal here, p, is a prime ideal. When we quotient this ring out by a prime ideal, we will end up with an integral domain. Okay, so the quotient ring, R quotiented out by P, will be an integral domain. Now that's not because the initial ring, R, was an integral domain, but because the ideal was a prime ideal. In an arbitrary non-zero commutative ring, when you quotient out by a prime ideal, you always end up with an integral domain. Okay, so this quotient ring is going to be an integral domain, and therefore, of course, when we take the ring of polynomials over that quotient ring, we'll also end up with an integral domain. Okay, so we'll use that in a bit, so I just want to point that out right now. Okay, right, so why then have I pointed out the fact that this interesting ring homomorphism exists? Well, of course, we're now going to apply it to this equation that I've got here. Okay, so we're going to take phi of p of x, we're going to map p of x onto what it is modulo the p, okay, the ideal p, and of course, because I now know that p of x can be written as a of x times b of x, where these are both polynomials in the ring of polynomials over my integral domain, I can say that this will be phi of a of x, and here's where I use the fact that it's a ring homomorphism to split it into phi of a of x times phi of b of x, where this multiplication is now a multiplication of the polynomials in the codomain ring here. Okay, so this multiplication, and I'll just put an orange dot there, and I'll underline this in orange. So this is multiplication in the codomain polynomial ring here, the polynomial ring where the coefficients are in the quotient ring are quotiented out by p. Okay, so what can I say that's interesting here? Well, let's firstly have a look at the left-hand side. When we take our polynomial p of x and map it onto what it is modulo this prime ideal p, we're going to end up with something rather interesting. And the reason is that we had assumed from the start that this prime ideal we'd found, it was the case that all of the coefficients except the leading coefficient of our polynomial p of x were in the prime ideal capital P. Now let me just draw you a little picture of the quotient ring. Okay, so here is our initial integral domain, capital R here, so I'll colour this in green here, like so. And then we've got our prime ideal in here as well, so here, let's say this subset is my prime ideal, and now what I've done is quotient out by the prime ideal to construct a new ring, and of course we know what that corresponds to. That corresponds to splitting the ring capital R into the additive cosets of the prime ideal capital P, and then defining an addition and a multiplication on those cosets in the normal way by picking representatives. Okay, now all of the elements then that are in the prime ideal P, they become one element. And what element do they become? Well, this prime ideal will always contain the element 0. So in fact this becomes the coset containing 0, and it becomes the additive identity in the quotient ring. Okay, so all of these coefficients in front of all the powers of x except the highest power of x are going to be mapped onto 0 in the quotient ring. Okay, so they're going to become 0 in the quotient ring, so they're just going to disappear. Okay, when we take the polynomial and map it into this ring of polynomials, where the coefficients are in the quotient ring, when we take the polynomial modulo the prime ideal P, all of those coefficients in front of all but the highest power of x are just going to go to 0. Okay? Right, so that's looking good. Now, the leading coefficient, where's that going to go? Well, the leading coefficient was 1 because p of x was monic. Now 1, where is 1 going to be mapped onto in this quotient ring, R quotient out by P? Well, it will not be in the prime ideal P, and the reason is that the prime ideal is a proper ideal. Okay, and the only ideal that contains 1 is the unit ideal, because the instant an ideal has to contain 1, because an ideal is closed under multiplication, it has to contain all multiples of any element it contains, and all multiples of 1 is the entire ring. Okay, so only the unit ideal contains 1. Okay, right, so 1 will be in a separate additive coset from the prime ideal, and it will be in the coset which we'll call 1 bar, which will be the multiplicative identity in our quotient ring. So the multiplicative identity in our initial ring is going to be mapped onto the multiplicative identity in our quotient ring, so that's fine. It's going to remain a monic polynomial, but it's going to be a much simpler monic polynomial. It's now just going to be x to the n. Okay, and you might now start to understand why this ring homomorphism between these two polynomial rings here might be of some interest to us because it simplifies the polynomial p of x so much for us. Okay? Right, now let's think then what we can say about these polynomials a of x, or rather phi of a of x, so the polynomial a of x taken modulo the ideal p, okay, and phi of b of x, the polynomial b of x taken modulo p, where the coefficients have all been turned into what they are in the quotient ring, okay, so which coset they are in the quotient ring. Okay, right, well what I claim is that we can conclude that the constant terms here have to be equal to 0 in both of them. Okay, now how can I conclude that? Well, it's best to actually write this out explicitly, so I'll write this over here. So we'll have x to the n, which is the left hand side here, is equal to our polynomial phi of a of x. Okay, and I'll write this a0. Oh, and I'll put bars. Okay, so I would have written the polynomial a of x as a0 plus a1x plus all the way up to let's say m, x to the m. Okay, but now of course it's phi of a of x, so all of the coefficients have been taken onto their cosets, so I'll just denote their cosets by the bar notation. So this is the coset that contains a0 bar, then we'll have a1 bar x here, and then it'll go all the way up to, let's say, am bar x to the m here, and then it will be multiplied by the polynomial phi of b of x here, which will be b0 bar, okay, plus b1 bar x plus all the way up to bn minus m bar x to the m. Okay, now of course the only, not x to the n, x to the n minus m there. Okay, so that these two terms here will multiply together to give this xn term. Now hopefully you should be able to appreciate intuitively here, and I'll give you a rigorous argument in a moment, but intuitively here, the only product that we want to be non-zero is this one multiplied by this one. Now intuitively, we are working with an integral domain here. Our coefficient ring is an integral domain. This quotient ring here is an integral domain. The entire polynomial ring is an integral domain. Hopefully you should be able to agree that the only way, see intuitively that the only way for you to multiply this thing and this thing together and just get this, just get the result of multiplying this with this, the two highest power terms here, okay, is if all the other terms are equal to 0, and therefore you can conclude that the two constant terms are equal to 0. Now of course that's just an intuitive argument. Okay, let me now give you a more rigorous argument as to why you can conclude that both of these constant terms, a0 bar and b0 bar, are equal to 0. Okay, so the reason you can do this is, firstly, of course, the constant term on the left-hand side is 0, and the constant term on the right-hand side is going to be a0 bar times b0 bar. Okay, now because you're working in an integral domain, you can conclude that if you've multiplied two things together and got 0, then one of them has to be equal to 0. Okay, so that then proves that one of them is equal to 0. Let's arbitrarily say that it's a0 bar that's equal to 0. So we've now proven that this one is equal to 0. One of them has to be equal to 0 from this. Okay, now that's gone then. You can imagine that having gone now. So we've now got this bit here multiplied by this bit here. Okay, now what's the lowest degree term then now? It's going to be this one here multiplied by this one here, because this constant term's gone now. So the lowest degree term in the product now is just going to be a1 bar times b0 bar. At least that's going to be its coefficient. Okay, and again you want that still to be equal to 0, and in fact what we're going to do is just work our way up here slowly and eventually prove that b0 bar has to be equal to 0 as well. Okay, so you're just going to work your way up now. This is the lowest degree term. We only want the highest degree term to be non-zero. Okay, so we want this to be equal to 0. Okay, so we want this to be equal to 0, and from that we can conclude that either a1 bar or b0 bar is equal to 0. Now I cannot conclude from that. That is not a proof that b0 bar is equal to 0, so we might as well assume the worst case, which is that a1 bar is equal to 0. I can't do anything else. I cannot just say b0 bar is equal to 0, because it's not necessary that that was the one that was equal to 0. So let's assume instead that a1 bar was equal to 0. Okay, so if a1 bar was equal to 0, then that's gone as well. So this one's gone. So now the lowest degree term of this product is going to be a2 bar times x squared times b0 bar here. And again, you continue this argument on, and you continuously say that these low degree terms, you don't want them, you want them to be 0. Okay, and you continue to go through all of the a's, and you'll say a2 bar has to be equal to 0, and you'll continue on, and you won't yet have proved that b0 bar has to be equal to 0, but then eventually you'll get up to this highest leading coefficient of the polynomial phi of a of x, and we do not want that coefficient to equal 0. am bar is not equal to 0 because that has to multiply with bn minus m bar to give 1. Okay, so these two multiply together to give 1. That means this is not equal to 0. But you do want it to be the case that b0 bar times am bar, which once we've concluded that all the other coefficients of a of x through this argument are equal to 0, is going to be the lowest degree term now. We do want that to equal 0, and therefore it must be the case that b0 bar is equal to 0. So there's your more rigorous argument as to why both a0 bar and b0 bar have to equal 0. Okay, so a0 bar needs to equal 0, and b0 bar needs to equal 0. Okay, so what we've now successfully concluded is that when we take these polynomials a of x and b of x, which we know are non-constant polynomials, okay, so they do have some coefficients of higher, of powers of x greater than x to the 0, okay, which are non-zero. When you take them modulo this prime ideal p, their constant terms are going to end up being 0. Okay, now what does that mean about the constant terms of the original polynomials ax, a of x, and b of x? Well, it means that a0 must have been an element of the prime ideal p, and b0 must have been an element of the prime ideal p. Okay, because only then would a0 and b0 have been taken onto the coset, which is the additive identity in our quotient ring. Okay, so we can conclude now that a0 and b0 are both in the prime ideal capital P. Okay, and now remember that p of x is equal to a of x times b of x. So the constant term of p of x is just going to be a0 times b0, the constant term of a of x times the constant term of b of x. Okay, so that now proves that p0, our constant term of p of x, is a0 times b0, but those two are both elements of the prime ideal p, and therefore that implies that p0 is going to be an element of p squared. So it's a nifty little argument, and that's a contradiction because we assumed that we had found this prime ideal such that the constant coefficient was not in p squared. It's a nifty little argument. I like the argument as to why Eisenstein's criterion is true. Okay, so we have now proven that Eisenstein's criterion does indeed work. When you have a non-constant monic polynomial in a ring of polynomials over an integral domain, you can conclude that it's irreducible if you can find me a prime ideal of your coefficient ring such that all of the coefficients except the leading coefficient are in that prime ideal capital P, but the constant coefficient is not in the prime ideal squared. Okay, you search through all the different prime ideals you can come up with. If you can find one for which that is true, you can instantly conclude your polynomial is irreducible. Otherwise, if it wasn't irreducible, you can conclude that, p0 was in p squared, okay, which is obviously a load of rubbish. It's a contradiction. Okay, so with that then we will finish this video on Eisenstein's criterion.